On the evening of June 7, 1942, a 4-engine Halifax bomber took off from Boscombe Down in Wiltshire, carrying 11 people, aircrew and passengers, on what was logged as a technical evaluation flight. Among the passengers was a 39-year-old electronics engineer who had already changed the way the world experienced music, contributed to the development of British television, and was now building something the Royal Air Force needed with a desperation that bordered on panic. Somewhere over the village of Margam in South Wales, one engine caught fire, the crew lost control, the aircraft went down, all 11 people on board were killed. The engineer's name was Alan Dower Blumlein. He held over 100 patents. His colleagues at EMI, the Electric and Musical Industries Company, where he had worked since the early 1930s, described him without hesitation as the most gifted electronics mind in Britain, and the device he had been testing in the blister mounted beneath the fuselage of that burning aircraft, a device that had not yet been deployed, had not yet been used in combat, had not yet done what it was designed to do, was a radar system that would go on to transform the entire strategic bombing campaign of the Second World War. The question, in the weeks after Blumlein was buried, was whether anyone could finish what he had started. To understand what he had been trying to build, you have to understand what was happening inside RAF Bomber Command in the summer of 1941, and why what was happening there was close to a catastrophe that the British government was not yet ready to admit publicly. The Royal Air Force had been bombing Germany since the first weeks of the war. The aircraft existed, the crews existed, the bombs existed, the political will to use all three existed, and by 1941 it existed in considerable quantity. Winston Churchill had staked enormous political capital on the strategic bombing campaign. The proposition that Britain could strike Germany's industrial heart through the air, even when it lacked the ground forces to threaten Germany by land. The campaign was the primary offensive arm of British strategy for a critical period when there was almost nothing else to point to, and so the bombers flew, and the crews reported their targets hit, and the assessors reviewed the bomb damage reports and filed their summaries, and for a considerable period everyone at nearly every level of the command structure believed the campaign was working. Then a civil servant named David Bensasan Butt sat down with aerial reconnaissance photographs from over 600 sorties conducted across 28 nights of operations. He studied the photographs against the mission reports, and what he found was so alarming that his report, delivered to Churchill's scientific advisor Lord Cherwell in August of 1941, was initially treated as too damaging to circulate widely. Of all the aircraft that claimed to have attacked their primary target over Germany, only 1/3 had actually placed their bombs within 5 miles of the aiming point. Not within 5 miles of the target, within 5 miles of the aiming point, which itself was sometimes just the general vicinity of an industrial city. Over the most heavily defended areas of Germany, the Ruhr Valley, Hamburg, Cologne, the fraction that got within 5 miles dropped to 1 in 10. The rest were dropping their bombs in darkness and cloud and dead reckoning hope, and the bombs were falling on fields and forests and villages and anything other than the thing they were supposed to destroy. 5 miles sounds like a large margin. Think about what it means in practice. A bomb that falls 5 miles from a factory does not damage the factory. It damages whatever happens to be 5 miles away. The crews were not cowards. They were not incompetent. They were navigating using techniques that had not materially changed since the First World War. Dead reckoning from a last known position, star shots when the sky was clear, timing and compass headings over featureless darkness, and then a best guess over the target when cloud, flak, and the natural chaos of combat had accumulated every possible source of error into one critical moment. A navigator who had been working for 3 hours in freezing darkness under sporadic anti-aircraft fire, having diverted twice around weather, having lost track of the wind drift over the Dutch coast, was not in a strong position to identify a factory from 6,000 feet in the dark. The wonder is not that 2/3 of the bombs were missing. The wonder is that any of them were not. Lord Cherwell presented the Butt report to Churchill. Churchill demanded a solution, and the solution, the technology that could actually show a crew what was below them in the dark, through cloud, through weather, through every condition that had been defeating them, was being developed by Alan Blumlein and his team at a requisitioned country house in Worcestershire, in an establishment so secret that most of the people working inside it could not tell their families what they were doing. Blumlein had not arrived at radar work through conventional channels. He had arrived because Britain desperately needed people who understood how electromagnetic signals behaved, and Blumlein understood electromagnetic signals at a level that made him, in this particular war, invaluable. He had been born in London in January of 1903, the son of a father with German Jewish ancestry and an English mother, raised in a household where he was clearly unusual, almost from the beginning. He studied electrical engineering at City and Guilds College, which would later become part of Imperial College London, and emerged with a first-class understanding of electronics at precisely the moment when electronics was becoming the most consequential field in engineering. He joined the Columbia Graphophone Company, and within a few years moved to EMI, where he spent the 1930s accumulating patents at a rate that astonished people who thought they understood what fast work looked like. By the time war broke out, he had filed over 100 patents. They covered telephone systems, audio recording techniques, radar principles, television transmission, and a technique he had developed in 1931 that would eventually be called stereo sound, the binaural recording method that captured music on two separate channels in a way that, when played back, gave the listener a physical sense of where each instrument was positioned in space. Every time you have ever heard music that sounded like the musicians were in the room with you, every live recording, every film score, every concert broadcast where you could close your eyes and place the piano on the left and the strings on the right, that spatial quality exists because of a patent Alan Blumlein filed in December of 1931. He was 28 years old. He considered it a reasonably interesting minor problem. He had already moved on to the next thing. When the war came, Blumlein moved into radar research with the same methodical intensity he applied to everything else. He joined the team working at what was called the Telecommunications Research Establishment, TRE for short, which had relocated from the south coast to Malvern in Worcestershire for security reasons. The establishment's project, by the time Blumlein arrived, was to produce an airborne radar system that could do something that had not been done before, paint a coherent image of the terrain below a moving aircraft. Existing radar at this point in the war was excellent at detecting discrete objects, ships, aircraft, coastlines, but it was poor at producing anything resembling a picture of what was actually below. The problem was wavelength. Long wavelength radar signals, which were what the existing systems used because they were easier to generate in useful quantities, spread over wide areas and returned imprecise echoes that told you something was there without telling you what it was. A long wavelength radar echo from a city looked almost identical to a long wavelength radar echo from a forest at the right range. For a navigator trying to identify a specific target, this was not helpful. The key to what Blumlein's team was building was centimetric radar operating at a wavelength of 10 centimeters rather than the 1.5 meters of the older systems. And here is the engineering insight at the heart of the whole thing, so let me explain it carefully. Think of the difference between trying to examine a coin by touching it with your whole hand versus examining it with a single fingertip. Your whole hand tells you there is something there, flat, roughly circular. Your fingertip tells you the exact edge of the coin, the ridges on the surface, the precise diameter. Radar wavelength works similarly. Shorter wavelengths are like the fingertip. They resolve fine detail, distinguish close objects from one another, return echoes precise enough to show you the difference between a river and a field, between a built-up urban block and an open area of parkland. Long wavelengths are like the whole hand, broad, imprecise, useful for detection but not for identification. The 10-centimeter wavelength that Blumlein's team was working with could produce a ground image detailed enough for a navigator to identify coastlines, rivers, lakes, and city blocks from thousands of feet in the dark. The antenna that generated this image was mounted in a rotating turret beneath the aircraft, spinning continuously, sending radar pulses downward in an arc that swept 360 degrees beneath the aircraft. Each rotation painted a line of returns on a cathode ray tube in the navigator's position. Over successive rotations, those lines built up into something that looked, if you understood what you were seeing, like a dim, slightly smeared aerial photograph of whatever was below. Not a photograph in any conventional sense, but precise enough, once a navigator had learned to read it, to identify major terrain features with a confidence that dead reckoning and starshots had never provided. The technology that made 10-centimeter radar possible, the cavity magnetron, had been developed by John Randall and Harry Boot at the University of Birmingham in early 1940. Blumlein's contribution was not the magnetron itself, but the engineering that turned the magnetron's output into a coherent airborne mapping system. The antenna geometry, the scanning mechanism, the display unit, the signal processing, the integration of all of it into equipment that could survive the vibration, cold, and electrical interference of an operational bomber. This is engineering of a kind that is easy to undervalue because it lacks a single dramatic invention at its center. It is instead the systematic solving of dozens of interdependent problems, each of which has to be solved correctly for the whole thing to work. The magnetron generates the signal. That signal is worthless if the antenna doesn't sweep correctly. The antenna sweep is worthless if the display can't render the returns. The display is worthless if the navigator can't read it in a darkened cockpit under combat conditions. Every link in that chain has to hold. Blumlein's team built every link. There was also the problem of what happened to the radar signal when it hit the ground at an angle rather than perpendicular. Conventional thinking in radar at the time assumed that useful ground returns required the radar beam to strike relatively close to vertical. Blumlein's team worked through the mathematics and discovered that angled returns, the echoes that bounce back from terrain off to the side of the aircraft's flight path, not just directly beneath, could be captured and processed in a way that extended the width of the image the navigator could see. Think of it as the difference between a torch that illuminates only what is directly in front of your feet versus one that spreads light across a wide arc on the ground ahead of you. Wider coverage meant more terrain context, and more terrain context meant that a navigator could identify a city's shape and river system from a much greater distance, giving more time to correct course and confirm position before the bombs needed to be released. This was not a small refinement. It changed the practical utility of the system from something that confirmed a target when you were nearly on top of it to something that gave a crew a genuine navigational picture across a substantial radius. The system had a name. It was called H2S, with the 2 written as a subscript in the chemical convention for hydrogen sulfide. The precise origin of the name is debated. One account says it stood for a description of the ground below as seen from the air, a kind of navigational notation. Another account, more often repeated by the people who worked on it, says the name was chosen because the system stank, meaning it was long overdue, that the need was embarrassingly obvious, and the delay in developing it had been inexcusable, and that hydrogen sulfide was the appropriate chemical symbol for something that should have been built years earlier. Given the Butt Report's findings, both explanations carry some weight. The Air Ministry's initial response to H2S was cautious to a degree that, in retrospect, looks like institutional paralysis. The specific concern was the cavity magnetron at the system's heart. The magnetron was the single most sensitive piece of radar technology the Allies possessed, and if an aircraft carrying it was shot down over enemy territory and recovered intact, Germany would gain access to the technology. The fear was not unreasonable. The magnetron's design was not something Germany had managed to replicate despite considerable effort, and losing it to a recovered aircraft over Europe was a genuine intelligence risk. The Air Ministry spent months debating whether to fly the H2S system operationally over Germany at all. Some senior officers argued that the risk of losing a magnetron outweighed the navigational benefit. Others argued that the system was needed so badly that the risk had to be accepted. While the Air Ministry debated, Blumlein's team continued refining, and it was during one of these evaluation flights that the Halifax carrying Blumlein and 2 other senior engineers from the programme went down in Wales in June of 1942. The loss of Blumlein very nearly ended H2S, not because no one else understood the system, there were other engineers on the team who were deeply familiar with the work, but because Blumlein had been the person who saw the whole thing in his head simultaneously, the engineer who could hold every interconnection in mind and know, when something in one part of the system behaved unexpectedly, what the downstream effects would be throughout all the others. The team that continued without him, Bernard Lovell, Philip D. and the remaining TRE engineers, described the period after Blumlein's death as one of the most difficult of the entire war. Not grief only, though there was grief, the sense that something irreplaceable had been removed from the middle of the mechanism while the mechanism was still being built. They continued anyway. They had to, and they solved the remaining problems partly from Blumlein's notes and partly from their own work, and by the winter of 1942, H2S was ready for operational testing. The first aircraft to carry it into combat were the Pathfinder Force, a specialist unit of Bomber Command, whose role was to fly ahead of the main bomber stream and mark targets with flares and incendiary bombs so that the following aircraft had something visible to aim at. The Pathfinders were the tip of the spear, the navigators on whom every subsequent aircraft depended for their targeting. If the Pathfinders found the target and marked it accurately, the raid had a chance. If they got it wrong, every aircraft that followed would add its bombs to someone else's wrong location. H2S gave the Pathfinders, for the first time, a genuine technical basis for knowing where they were over a completely darkened and cloud-covered Europe. The results were immediate and, to the crews who experienced them for the first time, almost bewildering. A navigator who had spent 2 years peering at charts in a frozen cockpit and guessing, honestly guessing, where the aircraft was, now had an image on a screen that showed the river bend ahead, the shape of the coastline behind, the radar signature of the target city growing on the display as the aircraft approached. The psychological effect was as significant as the tactical improvement. Crews who had known, in some private part of their minds, that their bombs were probably missing, described a shift in how they thought about their work. The sacrifice now had a visible connection to a result. Now let me put you exactly there. It is the last day of July 1943. You're the navigator in an Avro Lancaster of the Pathfinder Force, carrying H2S in a blister under the fuselage. The target tonight is Hamburg. Below you, somewhere beneath 12,000 feet of darkness and overcast, is the most important port in northern Germany, one of the largest cities in the Reich, home to the shipyards that are building the next generation of submarines, the oil refineries feeding the Luftwaffe, the railway yards through which supplies flow eastward to the armies on the Russian front. You have been briefed on the target. You know its coordinates. But coordinates are abstract. Germany below you is black. It is overcast. There is no moon. If this were 2 years ago, you would be staring at a chart and a compass and praying your dead reckoning was close enough. But you have the screen in front of you, and on it, dim, slightly smeared, pulsing with each rotation of the antenna beneath the fuselage, you can see the Elbe, the distinctive shape of the river as it curves through the port district, the strong return from the built-up area of the docks, the gap that marks the Ulster Lake in the city's heart. You know exactly where you are. You can place the markers, and you do, and the aircraft behind you will follow those markers, and Hamburg will burn tonight in a way that Hamburg has never burned before, and it will. The Hamburg raids of late July and early August of 1943, Operation Gomorrah, killed somewhere between 34,000 and 43,000 people, created the first true firestorm in military history, and destroyed a substantial fraction of the city's industrial capacity. The raids used H2S extensively. The navigational accuracy that H2S provided was a direct contributor to the concentration of bombing that made the firestorm physically possible. You cannot create a firestorm if the bombs are scattered across 10 square miles. The thermal column that formed over central Hamburg reached a height of over 40,000 feet, visible from 150 miles. Arthur Harris, the commander of Bomber Command, called it the catastrophe he had been working toward. Hamburg's Gauleiter Karl Kaufmann told Hitler the city was destroyed. But here is the part of this story that no documentary about the Hamburg raids will tell you. By the time those aircraft flew, the Germans already had H2S. On the 2nd of February, 1943, 5 months before Hamburg, 5 months before the system demonstrated what it could do, a short Stirling bomber carrying H2S equipment was shot down over the Netherlands near Rotterdam. The aircraft crashed with the H2S unit partially intact. German technical teams reached the crash site and recovered the components. Within weeks, a team at Telefunken under a scientist named Wilhelm Runge had the unit on a workbench and was studying it. They understood immediately what they were looking at. They understood the centimetric radar. They understood the rotating antenna. And they understood something that Blumlein's team, in the urgency of building the system, had not fully weighted as a vulnerability. The H2S transmitter, because it was active, because it was sending out radar pulses continuously, was broadcasting its own location to anyone with the right receiver. A system called Naxos was developed and fitted to German night fighters within months. Naxos was a passive receiver. It did not transmit anything. It simply listened for the 10-centimeter emissions that H2S produced. A German night fighter equipped with Naxos did not need to search for its target by conventional radar. It simply pointed toward the H2S signal and flew toward it. The bomber that was using its radar to find Hamburg was, simultaneously, advertising its exact position to every German night fighter in range. The scale of the problem became clear in the autumn of 1943, when Bomber Command's losses began climbing in ways that analysis could not entirely attribute to conventional flak or radar-guided searchlights. Night fighter kills were increasing. Crews were dying on routes and at altitudes where they had previously operated with a degree of relative safety. The intelligence eventually confirmed what some engineers had feared from the moment they understood how Naxos worked. The German night fighter force had learned to hunt on the frequency that H2S broadcast, and the bombers that most actively used their radar to navigate were in effect lighting themselves up. The device that Alan Blumlein had been building to let bombers find targets in the dark had become the thing that let German fighters find bombers in the dark. The Allies knew this was happening and could not easily stop it. Switching off H2S reduced the risk but destroyed the navigational advantage that had transformed Bomber Command's effectiveness. Flying with it on meant flying with a beacon. Some crews switched it off over the most heavily defended areas and back on at other points. Some units developed protocols for minimizing transmission time. None of these solutions were fully satisfactory. The fundamental problem that Naxos could hear H2S was not solved until late in the war, when modified centimetric radar operating at different frequencies partially addressed the vulnerability. It is worth comparing H2S directly to the other navigation systems Bomber Command was using at the same time, because the comparison clarifies exactly what Blumlein's system contributed and what it cost. G was a ground-based radio navigation system that allowed aircraft to fix their position by measuring the time difference between signals from 3 transmitting stations in Britain. It worked well, and worked accurately, inside its coverage area. The problem was that coverage area. G's signals were reliable out to roughly 400 miles from the transmitters in Britain. Beyond that, the curvature of the Earth degraded the signal. Germany's deepest industrial areas, the targets that mattered most, were at the edge or beyond G's range, and German jamming eventually reduced even that. G was a useful crutch for the early part of the outbound journey. It was useless over the Ruhr. Oboe was more precise than anything else Bomber Command possessed for marking specific targets. It worked by having the aircraft fly on an arc, equidistant from 2 ground stations in Britain, with signals from those stations telling the pilot when to release bombs. Accuracy was measured in meters, not miles. The problem with Oboe was that it could only guide one aircraft at a time, one aircraft flying one arc between 2 specific stations. Equipping an entire bomber stream with Oboe was not possible. It was used for the Pathfinder markers, precisely and brilliantly, but it could not scale. H2S had no range limitation. It worked equally well over Berlin as over Brussels because it was self-contained and required no ground station. It had no jamming vulnerability in the traditional sense, because it did not rely on signals sent from outside the aircraft. Its accuracy was lower than Oboe but higher than Dead Reckoning by a factor that had meaningful operational consequences, and unlike either G or Oboe, it improved with the skill of the navigator who used it. Experienced operators learned to read the ground returns with increasing precision over many missions, identifying features that novices missed. The German Knickebein and X-Gerat beam systems that had guided the Luftwaffe over Britain in 1940 represented sophisticated technology for their time, but they shared G's fundamental limitation. They depended on signals originating on the ground, which could be jammed, which required specific geographic configurations, and which provided no visual sense of the terrain below. H2S was a fundamentally different category of tool. Bernard Lovell, who had worked alongside Blumlein on the system and continued the program after his death, went on after the war to build something that most people would not connect to the airborne radar he had helped develop. He founded the Jodrell Bank Observatory in Cheshire and constructed the radio telescope that bears his name, the Lovell Telescope, completed in 1957 with a dish diameter of 76 meters, for decades the largest steerable radio telescope in the world. The design challenges Lovell solved to build that telescope, rotating a massive antenna, maintaining precise calibration in variable conditions, processing weak radio signals from enormous distances, were not entirely different in principle from the problems he had worked on with Blumlein in the Worcestershire countryside during the war. The wartime radar work did not cause Jodrell Bank, but it built the engineer who built it. H2S itself remained in operational service with the Royal Air Force long after the war ended. Modified versions of the system flew in British aircraft into the 1970s, and a variant designated 2S Mark 9 was fitted to Vulcan bombers, the nuclear-armed strategic aircraft of the Cold War era, until their withdrawal from service in 1982. The fundamental concept that Blumlein's team developed, a self-contained airborne radar that maps the terrain below and gives the crew a navigational reference independent of any ground station, is present in some form in every weather radar, every terrain-following system, and every airborne mapping technology currently flying. The navigation screen in a modern airliner is not the same instrument as the dim cathode ray display in a wartime Lancaster, but the principle descends in a direct line. Alan Blumlein's contribution to any of this was not acknowledged publicly until decades after his death. The secrecy that surrounded the work he died doing meant that the awards and recognition his colleagues received were not available to him, because the program he'd been central to could not be publicly discussed. His name appeared in some internal documents, and in the memories of the people who worked with him. It did not appear in newspapers or histories or any public account of the bombing campaign. His wife did not know, for years after the war, what he had actually been building in the aircraft that killed him. In 1971, nearly 30 years after the crash in Wales, the BBC made a documentary that was the first public account of Blumlein's wartime work. People who had known him and worked with him described him, after all those years, with the particular precision of people who had thought about what they were going to say for a very long time. One described him as the kind of engineer who made problems feel smaller, simply by being in the room with them. Another said that the work continued after his death, because the people who had worked with him felt, in some way that was difficult to articulate, that stopping would have been a greater loss than the one that had already happened. He died at 39. He never saw a bomber find a target using the radar he built. He never saw Hamburg. He never saw the Pathfinders drop their markers on a city that German anti-aircraft crews had believed was safely hidden by cloud. He never saw Bernard Lovell's telescope turn toward a sky that, in a different context and with different instruments, he had spent the last years of his life learning to read. They buried him in a country that was still losing the war. By the time it won, his radar was everywhere,